Oh. Okay. Well, it's sort of like the squawks. I hand this out in my freshman class. It's a list of real squawks from U.S. Air Force pilots to the ground crews. And these are actually things in the logbooks of the aircraft planes. And one of them says, IFF inoperative was the complaint from the pilot. And the mechanic wrote back, IFF usually inoperative in off mode. So, but there are other things like left engine missing, and the mechanic writes back, left engine found under wing after brief search. You know, but anyway, so we talked about activated diffusion bonding, how you can change a difficult to bond interface like aluminum or magnesium because of the refractory oxides. You can plate them with something else, nickel or copper or zinc or something like that. That would be a much easier thing to diffusion bond. And I gave you the example of a silver interface on two high-strength steel surfaces. We then started talking about soldering and brazing and pointed out that they're really the same process. They're ancient processes going back thousands of years. And the only difference really is the temperature at which the two of them operate. The American Welding Society chooses 800 degrees Fahrenheit. International Institute of Welding, being metric, chooses 425 C. And those are essentially the same temperatures, or for all intents and purposes. And there is a logical reason for that differentiation, aside from the fact that these two terminologies came up historically as people thinking of them as different processes. It turns out there is no braze alloy or solder alloy around that temperature. Nature has kind of left a void at that particular temperature range. It's not a complete void, because we could always design something in there, but in terms of common solders or braze alloys, we really don't have any in that particular temperature range. If you think about it, we have low melting metals going from tin and lead and bismuth. Zinc melts at something like 407 or 409 degrees centigrade. Aluminum and magnesium are around 660. And then you kind of jump all the way up to silver or gold or copper at around 1,000 degrees or 1,100 degrees centigrade. And if you alloy those with something else, you end up getting down to this temperature range where you just don't have very many metals that melt between 660 and 1,000 centigrade. Certainly no common metals in that range. I'm sure there's some praseodymium, or actually I don't know about praseodymium, but there's probably some transition metals that melt in that area, but who cares about europium and praseodymium and ytterbium and all those others. Now, one of the common problems in, well, actually before let me go through that. No, I will go. Oh, let me do it this way. We mentioned that you have to clean the surface in soldering, and typically we do that with a flux. And the requirements of the flux are that it have chemical activity. It's got to remove the surface oxides. Copper will develop surface oxides very rapidly. You know it as tarnish. And in fact, it develops those oxides much more rapidly than you tend to recognize in terms of the ability to clean something off. And I'm going to go, well, I will wait and do the other thing in a little bit. It also has to have spreading activity, or sometimes called wetting power, which means it must form a low contact angle. We've talked about how it's got to, the liquid solder has got to displace the liquid flux. And since we're usually soldering onto a piece of metal, if you have a liquid metal as the solder, that interfacial energy, being metallic bonding across that interface, is going to have a lower interfacial energy than if you had disomer bonding like a ceramic to a metal. So our fluxes tend to be ceramics or inorganic or covalently bonded materials, and our solders tend to be metals because we're trying to solder to a metal and we'll have a lower interfacial energy. And I'll give you an example of that in a second. You also have to have thermal stability. The flux has got to remain there in place. And that's not usually too much of a problem in soldering. I'll give you an example kind of an artificial thing where it doesn't work in soldering. It does create a problem a lot of times in brazing. People think just because you can kind of go to lab supplies and pick up a soldering flux and it will work for most of the solders you want to use. Because most of the solders you want to use probably melt between 200 and 300 degrees centigrade, or let's say 150 and 300 degrees centigrade. So that's not a very big freezing range, and you can typically use a simple flux for all those ranges. When you go to brazing, and now you're brazing between 500 or 600 degrees centigrade and 1500 centigrade, not all the fluxes, not a single flux will not fit all cases there. And so thermal stability of brazing fluxes tends to be more important than soldering fluxes. And finally, it should be non-corrosive or easily removed. And I'll expand on that here in a second. Let's go up to chemical activity. In terms of chemical activity, we've really got to have something that's going to clean the material and clean it well. And the question is, what do we mean by well? Well, the problem with most situations, or many situations, if you find that people are having soldering problems, the first question to ask is, when was the last time you cleaned your copper? And they'll say, what do you mean? I mean, it just came in the door, and we've had it sitting here for 6 months. You know, he's got some little electrical component, a resistor or capacitor or something, and they say, oh, well, you know, we received it this way. And you say, well, how old is it? Well, this lot just happened to be 6 months old. We usually get it in, we usually use it within 6 weeks, but this lot that's 6 months old, we're having problems with. Well, sort of a clue there that things get old, you have more difficulty soldering, just because you look at a doorknob, and there's more tarnish on it after 6 months than there is after 6 days. This comes out of a soldering manual, and it goes through, it's kind of complex chart, but here's freshly cleaned copper surfaces. Here's 24 hours in steam aging, here's 21 days, and here's 6 months. So I'm marching up here, and this is the wetting time in seconds of how long it takes for the hot solder to wet and start to flow across the copper. Now, a typical type of wetting time should be something less than a second. In fact, you'll see that if we have freshly cleaned copper, it really doesn't matter if it's, this is pure copper, unplated. This is copper that has a resin lacquer. We use rosin or resin for a flux, and I'll get to that later. This is tin-plated copper. This is gold-plated. This is a lead tin eutectic plated, and here's oh, this is roller plated. Don't worry about it. This same alloy. Here's tin plated gold, tin with a nickel underplate, and then a tin nickel gold type of underplate. So I have different types of surfaces here. Basically, I'm trying to solder to, and if it's freshly cleaned, which means I just dipped it in some little acid flux, the wetting of the solder on top of that metal will occur in less than a second. However, if I let it sit around for 24 hours, it turns out unplated copper takes more than 10 seconds. Essentially, it doesn't wet at all. The copper tarnished film, even though it still looks like shiny copper to you, it's not quite as shiny, and an oxide film has been growing for the last 24 hours. Yep.
24 hours steam.
That's steam aging, but it doesn't matter. In New England, it's always steam aged, right? No, this is accelerated, but I'm going to show you another plot that shows things are worse. If you actually have a solder surface of lead tin solder, which you're going to melt, this is lead tin solder on top of copper, you'll find that it doesn't matter even if it's 6 months old. So if I want to have good solderability, I already buy my components that already are pre-plated with solder. Because I'm going to melt the solder that's on the surface, the solder's already got a solder bond there. And you'll see that there is no waiting time or delay time here. If I get over here to tin nickel, you can see that you run into some problems fairly quickly, and that's probably because you end up growing a tin nickel alloy there. Well, actually, I might as well show this one now. This comes out of brazing and soldering books and the references in your notes. But this is, again, wetting time in seconds. Freshly cleaned copper is this thing down here, so it takes less than half a second. And I'll show you the test. It may not be until Monday, but one of the tests for soldering is just take a copper wire and dunk it in a pot of the solder and see how quickly it wets the surface. And we'll go through the way you can measure that in less than a second. But nonetheless, freshly cleaned copper does it in less than a second. And what they're plotting here is the amount of chlorine in the flux, because chlorides significantly improve the cleaning power of the flux, and I'll go through that later. This is 1 hour oxidation at 150 C and 2 hour oxidation at 150 C. You can see that if you're at pure copper, 1 hour at 150 C is going to destroy the solderability if you have no chlorine in your flux. If you're just using a straight rosin flux, and I'll talk about that in a second. So one of the requirements is you have to have good chemical activity to remove the surface oxides. And some of the fluxes that are most common don't have that. In addition, it's not uncommon for people to have a cleaning process for some part they want to solder. And this could be a printed circuit board, but it also can be bigger parts. People solder cans together and things like that. Transformer cans was another problem that I had once, where they were trying to solder and turned out it wasn't a solder problem as much as the base material and forming an intermetallic in that case. Well, maybe I'll give that example in a second. But the chemical activity, if I take something to a shop and I clean it and then I transfer it to another part of the plant to do the soldering operation, there are times that I've got to do all that transfer within 1 hour, basically, depending on the overall process that I have. Other times, I may have, if I'm going to store it, I may have to put it in a plastic bag to keep things from oxidizing, because of this growth of oxide film over time. And it occurs a lot faster than people often think. The spreading activity, the example there is if you were to take oxalic acid and use it as a flux. This is just an organic acid, a naturally occurring organic acid. There's a weed that always grows in my yard called oxalis, and it's high in oxalic acid. Commonly used in the laboratory for doing things like etching stainless steel and other things. But if you use oxalic acid on copper, you find that as you heat things up, things start to flow, and then it starts to spread, but then this little drop of solder will stop. And the problem is the melting point of the flux is 182 degrees centigrade. It starts to evaporate. It doesn't have a very wide liquid range. It starts to evaporate soon after that, and the melting point of the lead tin solder is 183 degrees C. So this is actually a situation where the stuff didn't stay in place. It didn't have thermal stability. The flux, this particular flux, doesn't have a high enough vaporization point. You can also use glucose as a soldering flux. Glucose is just a sugar, right? You could use sucrose if you want, but the particular place I got this example was using glucose on copper. It turns out simple sugar will reduce copper oxide, but the problem is it doesn't form the proper contact angle. And so when you melt the copper on there, and this whole thing would be coated with this syrupy sugar on top surrounding this. This would be the solder ball. It ends up staying as a solder ball. It doesn't want to wet the surface. The glucose has a stronger affinity for the clean copper surface than the lead tin solder does. If you look down on the top and you actually take that little solder ball with your soldering iron and move it across the copper pad, it will leave a little track of solder where it was in contact. If any of you are from the South and you know about slugs, anybody know what a slug is? Yeah, you know what a slug is. It's still a slimy snail without a shell, right? And it kind of comes crawling out after the rain, and they leave this slime track Well, this is just like a slug track on your sidewalk or something in the south, where the slug you can see his track because he leaves a trail of slime. Well, if you tried to solder with glucose, you would end up with what looks like a lead tin slime track sitting on top of the copper surface. Actually, I've done this with sucrose in the lab just to try it out. So if you want to try it out, get a piece of copper, put some table sugar on it, take a soldering iron, and make your own slime tracks. Then acetic acid, which is a complex acid, if you use that, it turns out you heat it up, and all of a sudden it starts to spread beautifully, and then it will kind of stop. It'll spread beautifully, but it won't go very far. And the problem is, it really has to do with the fact that acetic acid really has marginal ability to remove very much tarnish. It'll actually do a wonderful job at removing a little bit of tarnish, but it won't remove a lot of tarnish. And why are we interested in acetic acid? Well, it turns out acetic acid is the primary constituent in rosin flux. And if you go to lab supplies and you get some rosin core solder, or sometimes called resin core solder, it basically is the sap from a pine tree, and that's the rosin, and it contains acetic acid as a naturally occurring acid in the rosin. It has good viscosity, so it'll kind of stay in place. It has wonderful spreadability in terms of the surface tension balance. The lead tin just wants to replace it just fine. And if it's relatively freshly clean copper within the past hour, it'll solder just fine. But you try to do that a day later, just sitting in the air, and the pure rosin flux doesn't really work very well. And so if you put a drop of hydrochloric acid in that rosin flux, the spreading just shoots across the surface. And that's basically what this other curve is here. Is all you need to increase the solderability of rosin fluxes is just a little bit of chlorine, like 0.5% or 1%, or sometimes up to 2% chlorine. And now you can take a copper wire, which is what you're used to, and it's been sitting around for 6 months, and you can, you use some flux now, and the typical flux you get at lab supplies actually has got some chlorine in it. And it's typically not there necessarily as hydrochloric acid, it's there as amine hydrochloride. Now, if you want to know where other amine hydrochlorides are, go get some cough syrup at the drugstore, and that contains amine hydrochlorides. So maybe you can use cough syrup. So you can think of this as tree sap and cough syrup. But the cough syrup, or the amine hydrochloride, basically you now have a chlorine reaction with the copper oxide, forming copper chloride, which dissolves in the rosin just fine. And now it's really the chloride that's cleaning the surface. And then you can say, well, gee, that's great. I've never had a problem soldering things. In fact, if I'm a plumber, I go and I get a soldering flux at the hardware store, and I can take an old copper pipe that's been sitting around for years and is fairly tarnished, and I can solder to it if I have a decent flux that has 2 or 3% chlorine in it. If you really want a good flux, you go get something that's nothing more than zinc chloride and tin chloride and a little bit of hydrochloric acid, and that'll be a clear liquid flux, and that's typically used on soldering in pipes. The problem with that is, if you really want to make a good piece of electronics, a lot of your specifications, particularly your military specifications, don't allow it. No chlorine allowed. And one of the requirements of the flux, I put that one up, it's got to be non-corrosive and easily removed. Well, it turns out the copper oxide with chlorine forms oxychlorides. So I have not just copper oxide, but some complex oxychloride, and the oxychlorides are not very soluble in water. Turns out chlorides are very soluble in water. There's only one chloride that's not really soluble in water, one common chloride. Anybody know what it is? You did in high school chemistry, you didn't ever have to, in the lab, study, measure the chlorine content of something? what you do is, if you want to know how much chlorine, if you want to check the chlorine content of your orange juice or something, or Cambridge water or Cambridge air. One time I just condensed some Cambridge air to find out how much chlorine was in the air, to find out how corrosive it is since we're close to the ocean. Just condense some of the air, and you take it and you put some silver nitrate in. Ah, now you remember, right?
Oh, silver iodide, silver bromide, silver chloride, all insoluble.
Right. Silver. All the halides of silver are extremely insoluble. Silver nitrate is soluble, and so you put a drop of silver nitrate in there, and you will see in a clear thing of water, if you have very much chlorine, you actually see it turn cloudy because you're forming white precipitates of silver chloride or silver nitrate or silver bromide or whatever. All the other chlorides are very soluble in water and essentially can be cleaned off very easily. The problem is if there are oxides there too, which we know there are, you end up with oxychlorides which are not as easily cleaned off. And you might say, well, that's not a problem. It's a big deal. I got some oxychlorides there, except there is a reaction that takes place. We'll get to wave soldering in a little bit. And the reaction is basically that lead oxide plus chlorine ions give me lead chloride. I better put a 2 right there, right? Plus 2, let's see. Oh, just plus H2O. Plus water, right? And that plus CO2 from the air. So now I have lead chloride plus CO2 gives me lead carbonate. Oh, plus water. Plus chlorine. Hopefully I did that right. Well, no, not plus chlorine, plus HCl. Plus HCl again. Well, now that HCl, I've regenerated my HCl. You ever looked at a battery terminal in your car and see white deposit? It's lead carbonate. And it's there because if you're in New England and they put salt on the roads and you drive down the roads in the winter with the salt on the roads and it splashes up and you get chlorine on your battery terminals. And the chlorine on your battery terminals in the presence of moisture forms a little bit of hydrochloric acid. That reacts with the lead oxide on your battery terminals, forms lead chloride. The lead chloride now reacts with the CO2 in the air and the moisture to form this lead carbonate, which is a friable. Friable means what? Easily broken, brittle. A friable powder that if you touch, it just kind of falls apart. And if you don't go clean those terminals and rinse the chlorine off the terminals, and you come back a year later, you're not going to have contact to your battery because it's basically the presence of chloride. It doesn't take very much chloride because it regenerates itself in the process. So it turns out most military hardware, electronics, will say you may not use chloride containing fluxes in soldering your electronics. Well, if I can't use chloride containing fluxes, they just relegated me to working over here on this axis with no chlorine, which means that if I let things sit around for 1 or 2 hours, I may not be able to get solderability. The solder may not flow because the lousy rosin just doesn't have enough cleaning capacity for very tarnished copper. You need a freshly cleaned copper surface, particularly in military. The military handbook basically says no solder fluxes because they don't want to have this corrosion process takes place just in the simple. If you've got chlorine there, the moisture in the air, the carbon dioxide in the air are going to create this corrosion problem. And you've seen it on battery terminals, but it also occurs on electronics. So if you open up electronics that have been in a bad environment and you see little white deposits all over, it's just the lead and the lead chloride. No. There is, well, the way to fix it is, how to fix it on the battery terminal? You go to Pep Boys or some auto parts store and you get this little goo, this little jelly, which basically neutralizes all that. But it doesn't really fix it unless you really clean it off, okay? Well, baking soda will take it off, but that hasn't removed the chlorine unless you really wash everything down. And it'll just regenerate itself. If you don't get rid of the chlorides, it'll regenerate itself. Baking soda will help dissolve it, but and it'll also neutralize the acid a little bit, but the baking soda dissolves away too over time. No, the real solution, the solution for soldering of electronics is to use, well, in most commercial electronics, they end up using a chloride-containing flux, and they try to clean it as well as they can. Now, in times past, they used to clean it with Freon, because the Freons did an excellent job of dissolving the rosin with the oxychlorides and stuff. And then, what was the Montreal Protocol in '92 or whatever that outlawed Freons for air conditioners and everything else? And so they couldn't use Freon, and so that forced industry to go out and find some other chemicals, and they now have, they're actually still chlorinated fluorocarbons, but they're not, they've proved that certain types of fluorinated chlorofluorocarbons, okay? Basically, Teflon is a fluorocarbon, and Freon is a chlorinated, fluorinated hydrocarbon. Some of them do severe damage to the atmosphere, but others don't. And so they've now replaced all the refrigerants in your air conditioners with the ones that don't do damage to the atmosphere. And they have found similar types of things, although they tend not to be the fluorocarbons as much as things like citric acid-based things and whatnot, that actually do a better job of cleaning the printed circuit boards of the fluxes and things than the old stuff used to do. And this was a case where the Freon worked well enough and everybody was happy with it, and they never replaced it until they had, regulation said you have to replace it. And so they went out and they did research and they found things that worked even better. So now you go through a printed circuit board plant and you go through the soldering operation, and it smells like orange juice because they have these citric acid based solders. It's actually fairly pleasant. It's much more pleasant than it used to smell. Actually didn't smell too much. The Freons are very, very inert, which is one of their advantages. They have thought about using Freons and similar things as artificial blood. I remember one time I was developing a little model of a refrigeration system, and I was working with my students, and for whatever reason I was standing over this tank of Freon. We were about to transfer the Freon from the container into the little refrigerator we had, and for whatever reason something caused a squirt, and the Freon came up, and I had my glasses on, but it came up right underneath my glasses and just completely washed my eye. I mean, I didn't see it coming. It was kind of, it was peripheral vision, and it came up and it just squirted me, just completely drenched my eye. And first thing I thought, oh, I just got some chemical all over my eye. And we ran over to the eye wash station, and I started flooding it with water and stuff. And aside from the fact it made everything much cooler as it started to evaporate, so it's kind of like refreshing, right, in that sense. And it's wonderful at removing moisture from things. And so my eye was, I kind of needed to blink my eye to get the water back. And then over the next 10 or 15 seconds, I realized, well, this is Freon. This is one of the most, I mean, if there's been something else like sulfuric acid, I wouldn't have an eye. But you couldn't think of anything better to clean things with, in a sense, other than drying out your eye. And we got to the eye wash station, so it didn't dry out. Then Freon, it's completely inert. So I still have an eye. Although it kind of does argue for, when you're using chemicals, of using something than just regular glasses, because in that case it just, I had the glasses on. It didn't hit the glasses and get under. It kind of found its way right in there. In any case, if I'm going to do soldering of electronics, the typical way to do it nowadays, well, the way they used to do it 40 years ago, they had people sitting there with soldering irons, and they would solder each little lead together, and you had through holes in the printed circuit boards, and you put your resistor through there, and on the back side you'd have these little wires sticking up, and you'd want to solder those. Well, here's a printed circuit board we passed around before, and they still have through holes, but in fact they use both sides of the board now, and so they have to solder both sides of the board. And basically they glue the components to the surface, and then they, instead of having someone sit there with a little solder gun, they basically do wave soldering of these things. And wave soldering is you take your printed circuit board, which has its components glued on like this, and you pass it over a wave of lead tin solder. So if you go into a printed circuit board factory right now and go to the soldering area, they'll have this tank line that's about as long as this room, and the printed circuit boards go in one end, and usually for whatever reason the equipment's usually painted blue, but you'll just see these blue tanks. If you lift up one of the stainless steel tops, which you can't do while they're operating because the whole thing is in a controlled environment, they basically have about 1,000 or 2,000 pounds of molten solder being pumped up over a weir. So this is just a little probably steel or stainless steel trough, and you're pumping the solder up, and it's just flowing over the dam. Okay, everybody know what a weir is? A weir is kind of a dam that's too short and everything flows over it. And so you just have this fountain of solder, nice and uniform. Now you got to keep it clean, so they typically will have this in some sort of controlled atmosphere, maybe with a little bit of hydrogen in there. But they also will put a flux in there, which is nothing more than a foam flux. So it looks like a bunch of suds over here from your dishwasher, or some, actually from your sink rather than your dishwasher. And they foam the flux, this soldering flux, this acid type flux, and they bring the board in through here. The flux is heated, and so it preheats all the components, and you pass it by here. You have a slight angle of attack here so that the solder gets to each component. Now you can see there's all kinds of flow problems, and that the solder is going to want to hit this side more than the back side. And so you have to be careful about those things, and you have to design your circuit board so that you get good solderability all the way around, but you essentially solder everything at once. And then you put the components on the other side, glue them on, and pass them through again. Once you've soldered them, you don't need the glue anymore, but that's how you hold them on there. One of your homework problems asks you to calculate the minimum and maximum speed of wave soldering. Unfortunately, you find that the minimum speed is faster than the maximum speed, so there is no solution to that problem. I don't remember what I did wrong when I figured out the problem, but I decided I'd leave it in as one that has no solution, because sometimes in the real world there is no solution unless you change the whole thing in another way. So just be warned if you do the homework problems. Yes, I did make a mistake, but why bother to correct it? If it will confuse the students, then leave it there, right? So far as removing oxides in soldering, I can do chemical dissolution, which is acetic acid. Acetic acid dissolves copper oxide. It doesn't do it it can dissolve a lot of copper oxide, but its ability to chemically dissolve or chemically react with the copper oxide is weak unless you have a little bit of chlorine, just like in that corrosive thing. You want your flux to be non-corrosive, but you want it to be corrosive enough to eat away the copper oxide, so there's kind of a conflict there. You want it to be chemically reactive to clean the surface, but you don't want it to keep cleaning the surface afterwards. In fact, I remember someone in the Industrial Liaison program called up once from a company called Markham Corporation, and they said, we've got a problem. They make little label machines. If you go to the grocery store and you buy some meat and it's got a label on there, essentially they make the printer that prints the label. And they were making inkjet printers, print heads for these little grocery store type of label makers. And they said, we've got some lead tin solder joints and they're just corroding away in the ink at a tremendous rate. And I said, well, what's your ink made out of? And they said, acetic acid. I said, oh, well, that solves it. I said, basically what you've got is when this thing is operating at a higher temperature, it's a thermal print head for whatever reason, and they got acetic acid on top of lead tin solder joints inside the little cavity, and as oxygen gets in there and the lead oxidizes, the acetic acid in the ink dissolves it away. So the acetic acid, their ink was dissolving their solder. And I said, well, have you tried, you need to deoxidize your ink. You need to put something in your ink that's going to keep the oxygen level down. Oh, we've tried that and it improves things. Oh, well, okay, so at least we knew what it was that was causing it. I don't know how they finally solved it, but at least I was able to explain to them on the phone what the problem was, is acetic acid will dissolve lead oxide, and as long as they kept on introducing new oxygen into the system, the thing was going to keep on corroding away. In fact, that's actually not such a uncommon problem. A couple of years ago, someone brought me a copper, not a copper pipe, but a steel pipe. This is not soldering, but it was a steel pipe from their sprinkler system. And this was a wet sprinkler system, for your somewhere in here. We better have fire smoke sprinklers, don't we? I don't see sprinklers in here. Oh, yeah, there we are. They're right there. The white one right there, these are covered up. The little, it's between those two lights, okay? Actually, here's one right here. That little white plug that's about 2 or 3 inches in diameter, actually, that's a sprinkler, and it's a hidden sprinkler. If things come, it actually has spring-loaded and will come down and spray us all with water if you get smoke up there, or you get enough temperature up there. In any case, they brought in this little 10-inch length of pipe. It was about 1.5 inches diameter, completely just filled with iron oxide. It was just completely rusted through, hardening of the arteries. And I called them back. I said, "You've got a leak in your fire water system, don't you?" And they said, "How'd you know? This is a great big factory." I said, "Well, tell me about the leak." They said, "Well, yeah, we've had this leak for 10 years, and it's been dripping about kind of a little 1/4-inch stream of water, but we never fixed it. We just kind of let the water drain." I said, "Well, that's why you're going to have to replace your entire sprinkler system, because you've been reintroducing oxygen into the system with the water. I mean, there is oxygen in water. That's what the fish breathe. They may use gills, but they're breathing the oxygen in the water. And the reason you can use steel pipes in your boilers is because there's no oxygen in the water. You have to use copper pipes in your potable water because it's always fresh water that's got oxygen in it. So the water you drink, the fish can breathe in that water.
Dissolved oxygen?
Dissolved oxygen in the water. In your boiler system, you put in initially fresh water that has oxygen in it, but then it's a closed system. It's not an open system with fresh makeup water all the time. The closed system, what happens is the oxygen gets consumed, it reacts with the iron, but then the oxygen is consumed, there's no new oxygen, you get no more corrosion. Well, these people decided to take their closed system steel pipe sprinkler system and turn it into an open system. And guess what? They learned that iron corrodes in the atmosphere. Okay, water and oxygen will cause rust on iron. This is a new finding that, and it only cost, this was like a 100,000 square foot warehouse or factory or something. I said, well, next time fix your leak. Okay, sorry, you just corroded everything over the last 10 years because you've been introducing oxygen with your water the whole time. Now, it turns out we like to think that our copper pipes have corrosion resistance in potable water, but that's not true either. It turns out, particularly in New England where we have acid rain, Ohio generates electricity by burning coal, and that they put a bunch of SO2 up in the atmosphere, and SO2 with a little moisture forms sulfurous acid, which oxidizes to sulfuric acid, and it rains. And if you go measure the pH of a lake in New England or the river water, it's about 5.5. And no, it's okay. Tastes all right. I mean, Poland Spring, right? I haven't checked the pH of Poland Spring, see if they modify it, but if it really is pure spring water, it's probably slightly acidic. But don't worry about drinking something that's acidic. I mean, you're drinking orange juice, but if you drink Coca-Cola, Coca-Cola is about pH 2. It's an excellent paint remover, okay? It's basically phosphoric acid. So drinking something acidic is not necessarily so bad. Particularly, anybody know why drinking something acidic is not so bad? What's the pH of your stomach acid? It's about 1.8. It's hydrochloric acid about 1.8. And if you burp and get some bile up here, it doesn't taste so good because you have a stomach lining that protects you from the acid, and it's not supposed to be acidic up here, and that's why it's so irritating when your stomach acid gets up in the upper part of your digestive tract. But in any case, people think of copper pipes as being resistant to corrosion, but in fact they're not. In fact, you can pit through copper pipes in New England within 6 to 12 months in potable water. So if you live in Dedham, Massachusetts, where they live on wells, I mean, they're not part of the MDC water. I mean, I live in Belmont and Boston and a number, about 30 or 40 other cities during the Depression bought into the Quabbin Reservoir project, which was a WPA project. And you go out to western Massachusetts, they wiped out about 2 or 3 counties, and they built the Quabbin Reservoir in the Depression, and we have about a 10 or 20 year supply of water for these 30 or 40 cities in Boston. And so we don't really worry about droughts in those communities. Now there's communities right next to each other, right next to Belmont or Boston, like Dedham, Massachusetts, which they wanted to save some money during the Depression, and they didn't buy into the Quabbin Reservoir, and they have to take water out of the rivers and the lakes. And when they talk about a drought in New England, they're talking about the people who don't belong to the Quabbin Reservoir. And a lot of towns have been trying to buy into the Quabbin Reservoir ever since, and all the other people say no. Okay. But in any case, so the Quabbin Reservoir is going to be 5.5, and it's going to be acidic, and that acidity would pit through your copper pipes within 6 to 12 months. If you're getting well water out of Dedham, Massachusetts, it's some of the most corrosive water I've ever seen, and you have to treat the water you get out of your wells. If you're in North Andover, Massachusetts, or Andover, Massachusetts, they take water from some lake there, and they have corrosion problems. And that's because you have to treat the water properly. Here's your copper pipe. It turns out if you have the right amount of CO2 and pH and everything else, there's a whole bunch of things. There's solids in the water, alkalinity. There's about 5 or 6 different things that go into this formula that give you the Langelier index for the water. And the Langelier index is nothing more than a measure of the solubility of carbonates in the water. If the Langelier index is positive, it means you're going to precipitate out calcium, magnesium carbonate on the walls of your pipe. So you want a positive Langelier index. If the Langelier index is negative, it means that you will dissolve that other material, that carbonate. Calcium magnesium carbonate is more commonly known as limestone or dolomite. Actually, dolomite, if it's calcium magnesium